So welcome to module 6.5, and in this module we will be explaining project 7, which is essentially the translation process, the translation from the virtual machine instructions to the mnemonic of hack. Right? We have seen a set of examples and set of basic idea of how this will do, but now what we will do is to give you a very concrete explanation of this entire process. Right. So we have as a part of project 7 we will be basically handling two instructions, right, the stack arithmetic instructions, which are those 9 instructions: add, sub, or, and, these are bitwise or and bitwise and, then neg, not, then greater than, less than, and equal to. We have basically seen how these operations work, and then we will also be handling the memory calls, the memory access functions, which is push of segment index and pop segment index. And we have also seen there are 8 different segments: a segment that will hold the arguments, a segment that will hold the local variables, then 2 general purpose segments, this and that, and then there we have a temporary segment which is stored in the RAM between 5 and 12. So we have 8 locations in the temporary segment, and then we have pointers to the this and that, we call pointer segment, and then of course constant. So the segment here in the case of push can take any one of these values, 1, 2, 3, 4, 5, 6 and constant. Okay, so and static, of course, any one of these 8 values this particular segment can take. So what push means is that the value from this segment, whichever segment plus index, need to be pushed into the stack. Pop is from the top of the stack, remove an element and put it into the value given by the segment. So the address pointed out by the segment index, you have to take from the stack and put it here. Now this segment, in the case of pop, we cannot have it as constant, because I can't take a value and put it in a constant, right? So for pop, constant doesn't exist, but for push all the 8 exists, 8 different segments exist, and for the pop there are 7 segments except constant. And so these are the type of legal instructions that we will see in your VM file, and every such instruction we have to translate it into the corresponding hack mnemonic, and that is all about project 7. It's a very easy project, it hardly takes 1 hour for you to complete. I'll tell you how to go about it, and then you can take it forward. And at this time, this is exactly the time where we talk about compilation. One important thing is that when we surveyed many of the education curriculum, especially in the case of compilers, the backend, a compiler has 2 parts. One thing is you have a language, you do a syntactic analysis, you do a parsing, then you actually generate an intermediate representation, and from there you do something called backend, which is basically you translate that code into the assembly language, the real translation process, the assembly language of the target architecture. What we are doing here is essentially the part of that backend where we are taking the translated code, we are taking the virtual machine code, which is actually intermediate representation. So Jack is the original programming language, we have the compiler will convert it to that intermediate representation. Now we are taking that intermediate representation and getting onto the mnemonic. So that is the backend process is basically done here, and this is the point where we need to study about compiler optimizations and so many things, and many curriculums actually do not have big emphasis or give lesser emphasis for the backend. It's very important that we learn backend, because backend is one that is going to become extremely important especially when we now talk of varieties of processors coming up and specifically targeting different types of applications, etc. Backend becomes extremely crucial. So this particular project 7 is very, very important for any aspiring computer scientist or computer engineer. Okay, so let us give our full effort and see how we go about this particular problem. Right now, let us understand the VM instruction in its full glory. Right, so we have been talking about that bits and pieces. I am sure you will have a vague idea now. I want to concretize that idea. Whatever you have, you should be crystal clear of what every instruction is supposed to do. And to aid this, so there is a tool that is given as a part of the software, which is called the VM emulator, the virtual machine emulator. Now we will use the VM emulator and basically tell you how things will work. Now we have already explained that when a particular program starts executing, when a function starts executing, the function will have different types of variables. Like it will have local variables which is stored in the local segment, arguments that are passed which is stored in the argument segment, and then it will ask for some extra space through malloc, and those two segments are this and that, and then of course for doing all the arithmetic computation, this being a stack based virtual machine, will use a stack. Now so there are 5 different areas of memory, what we call as segments of memory, where the values of the local variable, arguments, this, that, and stack, all this would be stored. Now when the architecture is executing, it needs to know where the stack starts, that's the base address, right, and where the local segment starts, where the argument starts, where the this, if at all I am using it, where it starts, that where it starts. So those base addresses of the stack segment, local segment, argument, this, that, are stored in your data RAM in the locations 0, 1, 2, 3 and 4. So please, this stores the base address of the stack, right, and then there is a temporary segment which we can again use. In addition to this and that, the compiler can use, the machine can use a temporary segment. The temporary segment of memory has 8 locations starting from 5 to 12 in the RAM, the data RAM. You have instantiated the data RAM, and in the data RAM, this 5 to 12 will be for temporary. And this 13, 14, 15 are again registers or temporary, we call it as scratchpad memory, which is again free. Anyone can use it, and it's just a scratchpad. So we can just use it again. Okay. So essentially, to have a so this is how you understand this whole thing, right? So I have these segments, the base addresses are stored in 0 to 4, then I have a temporary segment which has 8 locations. I can store any data and retrieve it. The temporary data segment is between 5 and 12, 8 of them, and 13, 14, 15 are still scratchpad, which still I can use it, right? And when you actually did the assembler, you have assigned this as, you know, R5. So from here, right, R0, so R5 to R12, this is R13, R14, R15. If you go to your symbol table, you would have mapped R13 to 13, R14 to 14, R15 to 15, right? So if I want to access this location, so how do I access R13 if I want? I just say at R13. The moment I say at R13, your A at register will get 13, because at R13 is in your symbol table, it is mapped down to 13. Now I say M, then M means M of A, so this whatever value in this 13 will come out. So if I say D equal to M, then I can actually read the value that is stored in 13. If I say M equal to D, then I can write whatever is there on the D register onto this M, and all these operations I can do. So this is one simple understanding that we need to have before we start using the emulator. Now we will start using the emulator and run some interesting code here. So how do you invoke the emulator? Right? So I'll though I brought it here, I'll again start from the beginning. How do we go and import the emulator? Okay. So, go to your NAND to Tetris directory, go to your tools, there is a VM emulator dot Windows batch file. If you are using Linux, you can use .sh. If it is Windows, use this VM emulator. Okay, your emulator has come up. Okay, it doesn't matter. Now let us take some programs here. So load a program, right? So I can load a program. Yeah. So when I say push constant 17, 17 gets pushed into the stack, and this is 0 is there at 257. The stack segment now points to 257. So 17 is pushed into the stack. Again I do push another 17. So 17, so your stack now becomes 258, your stack pointer becomes 258. It is in RAM 0 again. Now I am doing EQ. What will EQ do? It will compare whatever is there on the top of the stack, namely at 257 and 256, and if they are equal, then it will pop them out. So you will now see 256 as -1. What is -1? 1 1 1 1 1, that is 2. So now let us do this EQ. So from the stack, as you see, both the 17 are matched, and the answer is -1, and the -1 goes back to the stack pointer. Now the stack has -1 alone, and your stack pointer now is in 257, right? So this is what basically happens here. Now I am now trying to push 17 now. So 257 will again get 17. Now 258 will get 16. Now we are now going to compare EQ. What will then that means 257 and 258 will be compared, and if they are equal, they are not equal, then so essentially now we have to get in 257 we have to get 0, that is false, because we pop these two values and then compare, and then whatever is the result we store here. Now we do this, right. So first 16 is brought down, that is Y, then 17 is brought down, they are compared for equal to, they are not 0. Now 0 goes back and stays in the stack, right. Now again let us do this. Now your stack is at 258, now 16 is pushed, so 258 will get 16. Now 17 is put, so 259 will get 17. Your stack pointer now is 260. Now again I am comparing EQ. Now you say 17 goes up, 16 goes up, 16 is X here in this case, answer is 0, and the 0 is pushed. So now your stack pointer is 259, because 256, 257, 258 are full. Now I push 892, I push 891, now I say less than again. So less than, we have to be careful. Please note that X is to 892, Y is 891. So I am comparing 892 with 891 for less than. Obviously 892 is not less than 891, and so you should get 0, and that 0 will now go and stay in 259, and your stack pointer should become 260 after this operation. So let us see that. So 891 is Y, 892 is X, we have already explained that. So the answer is 0, and that goes there, and your stack pointer now is 260. Now again I am pushing 891, 260, 892 into 261. Now I am doing again a less than here. So 892, 891. Yes, 891 is less than 892. So the stack should get -1. So stack gets -1, and we are at 892. Now again we do the same thing. 891, 891. Now less than, we compare. 891 is not less than 891, and so I need to get a 0, and the stack now becomes 262. Now I compare 32767 with 32766 for greater than. Yes, Y is 32766, X is 32767, 32767 is indeed greater than 32766. So the answer is -1. -1 is true. 11111. The decimal 2's complement of that. And then your stack now should point to 263. So 263 is now having 32,766, but that's part of the previous computation. So when I get out of the stack, I will not, when I pop something, I am not going to erase that. I am just reducing my stack pointer, right? And the next time, so if I am pushing now, again I am pushing 32766, so 32766 again comes here, right? And 32767 is loaded. Now we are saying greater than. Now obviously it is 32766 is not greater than 32767, so I get a 0 there. So 263 becomes 0. Now the stack is 264, but originally stack was 264th location was used for storing the 32767. We have not removed that 32767, right? So something that was used in the past is still left over in the stack, right? What we said that when popping means I reduce my stack pointer. So the fresh thing, like I am now going to write 32766, that 32766 will replace this 32767 as you see here. But the original 32767 was not removed, right? Now this is one major issue when we come to information security, right? So when you take advanced courses in information security, what would happen is that something that you have written in the stack, when you popped out of the stack, you don't erase it, like we are not erasing it here. And since you didn't erase it, some other process which is trying to access may get the same stack, and they will see all these values that you have used which are not erased, and that is how some of the critical information like password etc. can leak out. So this is one very important thing. So when you actually write a compiler with a secure compiler, right, when that secure compiler should say whenever I pop, you should make it 0 and then only pop. So this 32767 should not have been there when the moment I popped. Now in this operation also you will see 32766 is loaded into 265. Now I am seeing greater than. So obviously 3276, you can see the animation that's happening, very nice one, right? So 264 became 0 because 32766 is not greater than 32766. So that operation got over, but still the 32766 is still there, which is used in the previous operation. Though I am going to replace it with now 57 now, right? But it is still there. So this is one thing, when you write a secure compiler, it should not be there. You should make it 0. Otherwise, the next process, this information will be available in the memory, and some other process which will use the memory later can basically get out the critical information. Suppose you store password instead of numbers here, then it can go out. So this is one very important clue that you keep in mind, right? Now let us go and see. Now I am going to push 57 inside, yes, then I am pushing 31, then I am pushing 53. These are all constant push. Now I am going to do add, which will add 31 and 53, 84, and it will make 266 as 84, and my stack should become now 267, right? So this is how it will go. Sorry. (53 plus 31, 84 now goes back into the stack. Note that 53 is still here, but this is what 84 is the answer. Now I am pushing constant 112. Now I am subtracting 84 from 112. 112 from 84. X is 84, Y is 112. Always that's the syntax. So when I do a subtract, 112 is Y, 84 is X. 84 minus 12 is minus 28, so minus 28 will take the position of 84, and your stack pointer now is 267. Now I do a negate. What will negate do? It will go and make the element on the top. What is there on the top of the stack? 267 is the stack pointer. Always the stack pointer will point to the location where I can enter something fresh. The top of the stack is 1 less than that stack pointer. Again, you should remember that. So minus 28 is on the top of the stack. Now I do a negate, it should become 28. So minus 28 comes here, it's a unary operation. I negate and then 28 goes back to the stack. Now I am pushing constant 82. Now I am doing an AND. So I am taking 57 and 28 and we are getting 82. 57 and 28. So for doing this AND, probably we can use it as binary. Then we could have appreciated this. I don't know whether we can backtrack this. Let me see. No, I can't backtrack. So 57 and 82 got AND. So then it became. So let us go back. We will explain the R much more. Now I am pushing 82 inside to the stack. Yes, your stack is now 267. Now I am going to do an OR operation. So let me just do binary. So what will OR do? It will take the top two fellows and do an OR of this. Okay. So let us do how it is going to do. 266 and this has gone, and so it is 90. So and we have got this 1011010. So this is the R. Right? Now again I changed that format to this one. Now I am going to do a NOT of 82. Oh, that's interesting. So I just do NOT of 82. So I should get all 11111110. Okay. So I just do a NOT. So this becomes minus 91 in 2's complement arithmetic. Okay. And that's it. So this is how these things work. So when I push, what it means to push something, go to your RAM location 0, that is at SP, means your RAM location 0, read the content of RAM location 0, that will give you the stack pointer, that address will be the stack pointer, and if I am doing a binary operation, go to the one address below it, get the first, get Y, one more address below that, get X, do the operation. If it is a unary operation, go to that point and then after that reduce the stack pointer. That means go back to the 0 and decrement its content by 1. That is what you mean by reducing the stack pointer. So this is what you do in the case of binary operations. Right? In the case of push operation, what you do? You go to the stack pointer, whatever is the memory location, go to that memory location and write whatever you want into it, and then go back to the 0 location and increment this value, say from 266 to 267. Right? So these are some of the things that we are getting. And this understanding you need to get out of this. So let us do some more of things. So we have done stack test. Let us do, say, we'll go up. Let us do memory access. This is very interesting. So let us go. So this is the program. Again, note that your stack segment is initialized to 256. Let us go one by one. Push constant 10. You know what will happen. So pop local 0, right? Pop local 0. The local segment starts at 0. That 0 plus 0 is 0, because what is the base of the local segment? It is 0. That 0 plus 0 is 0. So you pop the value of the stack, that is from 10 on to 0 plus 0, 0. So your stack pointer now should become 10. That's what should happen. You understand? So local is a segment its base address is 0, I add 0 to that, that is 0. So, that means the address to which I need to pop is 0, and what I will pop 10. So, now your stack pointer should become 10. Let us see whether it is happening. Now, what are we understanding? See, I have to, when the system boots up, the operating system, we have to allocate some space for the local segment. Everything I have made 0. So, this obviously should not work, right? Right. So, let us reload this program again. And then we should also look at the script. Okay. Now, this is something very interesting. Load the script, and there you see what are the things that need to be set. So, my RAM 0 basically is 256 for the stack. Now, I will go and set my local segment as 300. We have to set the local segment as 300 and my argument segment as 400. Everything cannot be 0. So, I have to allocate memory when the program starts executing. I need to allocate memory for that function. I means who? The operating system has to allocate memory for that function for storing the different segments. Otherwise, things will not work, and that is what I demonstrated here, right? So, I make this as 3000 and that as some 3010. Okay. So, this is something that we need to load. Okay. So, what I have done here is as follows. The stack is 256. This particular program is actually going to read from the local segment. There are some local variables. So, for the local variable I have to set I have to allocate space. So, I say let your local segment start at 300. So, anything that I want to write, local segment will be from 300, and your argument will start at 400, your this will start at 3000, and your that will start at 3010, right? And temp always will start from 5 to 12. Okay. Now, let us reload this program. Load program. We have loaded the program. Now, let us go and set all these things. This should be 300, this should be 400, this should be 3000, this should be 3010. Okay. And now, let us start executing. Push constant 10. Yes, 10 gets pushed into the stack. Pop local 0. So, local is at 300, right? Local is at 300. So, 300 is the base for local plus 0. So, the address to which I need to pop is 300. In the 300th location, I need to pop the value. What's the value? So, the 300th location will become 10 and your SP will again become 256 after this. Let us see whether it is happening, right. As you see here, yes, your 300th location became 10 and your SP has become 256. Let us see what has happened at the 300th memory location. We can go down here and you can see that the 300th memory location has become 10. So, this is how it popped. So, what does pop do? First it will go, it will find which segment you want, that is local, it will take the base address of that local, add with that index, it will find the address to which I need to pop, that is in this case 300. Now, it will go to SP, right, it will get the stack pointer value, it will go one below that stack pointer value, whatever value is there, it will now go and put to the calculated address, in this case 300. So, 10 goes to that address and now I decrement the stack pointer. Now, stack pointer is now 256. So, stack is actually empty now. Now, I am pushing constant 21. So, 256 gets 21. Now, 256 will get 22. Now, I want to pop this to argument 2. Argument, so where does argument starts? Go to RAM location 2 and you find that address 400. 400 plus 2 because you said pop argument 2. So 402, now I need to go to 402, and in 402 I have to pop 22, and your SP will now again become 257. So your 402 will get 22 and your SP becomes 257. Let us see that. So in your argument 22 comes and it becomes 257. Now if I go and see 402, right, if I see 402, you get 22 here. Similarly, pop argument 1. So in 401 you will now get 21. 401 you should get 21. And your stack now has again become empty. That is, it again points to 256. You push two constants and you popped. Now I say pop this 6. Whereas this, go to location 3. Again in the assembler symbol table you have marked this as 3, right? Go to that 3. So that will be 3000. 3000 plus that 3000 plus 6. 3006. 3006 should get the value 36 now. We have actually pushed constant 36 there. Now 3006 should get the value 36. Now let us see. So we have only till 2000. Oh, this is a global stack. Oh, this is a RAM. So 3006. Be careful in just scrolling this. I can just, so I am just giving you, so just scrolling will become extremely complex, like it becomes slow. Now I can go and say, so 3006 gets 36. I can use this search option. Okay. Now again push constant 42, 45. Now pop that 5. So that is at 3010 plus 5, 3015, you pop 45. So 3015 should get 45 and 3012 should get 42, because you do pop that 5 and pop that 2. Let us do that. So how did you calculate this 3015? Because that in the assembler symbol table is 4. So go to that address 3010, add 5, 3015, then you pop to that and 3. So let us go and search for 3015 and 3012. .45, and you also see 3012 getting 42. Yeah. Now let us do the next one. Pop temp 6. Temp is an array. As you see, temp will always start from 5. So now that 510 which is on the top of your stack should go to, the base address of temp is always 5. 5 plus 6 is 11. So into the 11th location 510 should go. Let us see where that's going. So on the 11th location in the RAM you get 510, right? And then the stack actually gets popped. So the difference between the other things that we have seen, like pop that, pop argument, pop local, is I go to the location, from there I get the base address, and then I add that base address to the index and then push or pop to that from there. But here when I say temp, the base address is already given, so that is always 5 for temp. So I just add 5 with that 6, so I need not do one additional memory access to find the base address. Base address is by default 5, right? Now push local 0, local is 300, so what is there in local 0? That is 300, we have 10, in location 300 we have 10. That 10 will now get pushed into the stack, and the stack will now become 256. Let us see whether it is happening. That is 3010, that plus 5 is 3015. So in the 3015 there is 0, right? So 3015 currently has 0. 3015 currently has in that, right? 3015 currently has 45. Now that 45 has to get pushed onto this stack, right? Push that to that plus 5. 45 essentially has to get pushed on. Right, 45 gets pushed on. Now we need to do add. So this 45 plus 10 should become 55, and the stack pointer should become 257 now. Let us see that happening. Yes, done. Now I say push argument 1. Argument 1 is 21. Argument 1 is stored at 401, right? 401 has 21. The base address for arg is 401. So 21 essentially comes here. Now I do a subtraction of x minus y. So this is x is 256, y is 257, right? So 55 minus 21 should essentially become 34. This segment is stored at 3000, so I have to push this value to a 34 to 3000 plus 6, 3006. Sorry, whatever is there in 3006, which is 36, will now get pushed to the stack. 3006 had 36, right? 6. And again I am pushing the same, this plus 6, another 36 I am pushing. Now I am subtracting these two, first y, second y. I am adding these two, I get 72. Again I push it back into the stack. Now I am subtracting these two, 72, 36, 34 minus 72, that will give me minus 38. Now I am pushing temp of 6. Temp of 6 is 510. Please note here you are seeing that 510. We are adding that, minus 38 plus 510. 472 should come back there. And that's the end of this code. So I am going through this very slowly because we try and get to understand how the entire virtual machine works. We have to do two more code here, so please bear with me for this. This is pointer test. So we will again set this up. This has 300, this has 400, 3000, 3010, whatever. Okay. Now push constant 30, it's gone in. Your stack pointer has become. Pop this to pointer 0. So what is pointer 0? Pointer 0 is the value of the base address of this. Please understand this. This we have been explaining in detail earlier, but we will concretize that explanation. Pointer 0 is nothing but base address of this segment. Pointer 1 is nothing but base address of that segment. Okay. So when I say pop pointer 0, that means whatever is there on the top of the stack, that is 330 should become the base address of this. The base address of this is stored in 3. So location 3 should now become 3030. Let us see if it's going to happen. Yes, look at the animation. Yes, it's going to become 3030. And the stack is now popped off. Now push 4040. Now if I say pop pointer 1, the base address of that should become 3040. Let us say it's going to happen. Yes. It becomes 3040. Now pop this push constant 32, pop this 2. What is this now? 3030 plus 2 is 3032 into location 3032, write 32. So 32 will be written into 3032. So now we can see search for 3032, you will get 32. Okay. Push constant 46, 46, push pointer 0. Push constant, pop that 6, right? Pop that 6 will become 46, that is 3040. So 3046 will get 46. 3046 will get 46. Yes. Now we will say push pointer 0. Pointer 0 is the base address. Now 3030 will be now pushed into the stack. 3030 gets pushed into the stack. Push pointer 1. 3040 will be, pointer 1 is the base address of that. That means pointer 1 is always 4, pointer 0 is always 3. So whatever is content of RAM location 3 will go to the stack and vice versa. Now I will add this, so this will become 6070. Now the stack is now having only one element. Now push this 2. What is this? This 2 has 32. This is 3030. This 2 is 3032 and it has 32, right? So 3032 now will go into the stack. Now I will subtract this. So this will now become 6042. Sorry, 6038. Sorry. and then push that 6. That is now 30, 40. So 30, 46 I will push whatever is there in 30, 46 I will push. In 30, 46 we actually have 46. That 6 we have 46 as you see here. Okay. So that 46 will now get pushed. Now we add these two. This will give you 84, 60, 84. And that's it. Okay. And the last program that we will see before we wind up, if you are feeling bored, but please bear with me, but please understand this, because anything tough will come with a pinch of salt. Now you need to have a lot of patience to understand and take it forward. So static is very, very important. So where will the static segment start? In your assembler, normally it starts assigning variables from 16, right? If you remember, if it finds some variable, it will start. Everything else is in the stack. What will be normal variables? If they are actually local variables, they will be in the local. If they are arguments, they will be in the arguments. Other than local, argument, etc., the other variables that are not there or not mapped to local and argument, they are all going to be static variables. And your compiler, in your assembler, for all the variables that it sees, right, it starts allocating location from 16, etc., right. So in this case also we will assume that, so let us see what's going to happen in this case. First we are pushing 111, then 333, then 888. Now I say pop static 8. So where will static 8 do? Let us see what's going to happen. So basically this should have gone to location 23 or 20, it's going to 24. 16, so you start assigning from 16, 16 will be static 0. So 8 variables, so it's go to 20. So all the static variables you start assigning from 16 onwards. Okay. So essentially this goes there. So when we are doing the translation, since we will just leave it as that variable name, or some will give a variable name, because automatically the assembler will do this allocation. So when we do the translation, we need not do the allocation for static variable. We will just say some variable name, and automatically the assembler will do assign this, say 16 to 16, right. Similarly, pop static 3, so 333 should go to 19. Yes, 333 got 19, got 333. Similarly, static push static 3, so 333, the pop static 1, so 17 got 111, right. And now push static 3, so 333 should get into the stack, and sub and push static 1, so 111 should go there, and then I do a subtraction. So 111, 333 is X, remember that. So 222 should be now on top of the stack, and top of the stack again now is 257, because we popped those two values and pushed this. Now push static 8, it is 888. Now I do an add, this should give me 1110. Yeah, good. So what we have understood so far in this thing, thanks for your patience. I think we have now understood very clearly how these memory stack arithmetic and memory instructions work. Right? Now we will quickly go into how we are going to translate these instructions.